Okay, this is the last hour of Physics 1C for September 20th, and the last hour we're going to talk about what's called conductors and electrostatic equilibrium. We're mostly going to be looking at properties of conductors when they carry charges. What happens to conductors when they carry charges? In the interest of getting all of these details right and keeping them in a way that you all can read them, these are the four properties that we want to talk about. And the way that I'm going to do this is I'm just going to try to prove to you that each one of these properties is true, as opposed to doing the opposite. So this is what we want to prove. We want to be able to prove that, number one, the electric field is zero everywhere inside the conductor, whether the conductor is solid or hollow. We'd also like to prove that if the conductor is isolated and carries charge, the charge is going to be on its surface. And then we want to prove that the electric field at a point just outside a charged conductor is perpendicular to the surface of the conductor and has a magnitude of sigma over epsilon naught, where sigma is the surface charge density at that point. I will prove all three of those. We'll talk about number 4, but I can't prove it until next week. Okay, the first one. The electric field is zero everywhere inside the conductor, whether the conductor is solid or hollow. To prove this one, I often like to prove the second one first. I'm trying to think about how we could prove the first one without assuming the second one's true. So let's start with number 2. Let's prove this one first. No, we can do let's do number 1 first. I just realized there's a way we can do this. Okay, so the electric field is zero everywhere inside the conductor, whether the conductor is solid or hollow. Okay, so let's start off by drawing a conductor. So we have some irregularly shaped conductor. When I say conductor, you should basically just think that it's a metal. And let's start off with talking about a solid conductor, okay? So a solid conductor would mean that it's just some mass of metal. Okay, so just imagine any piece of metal you have ever seen before. It could be, like, I'm looking at my door. My door has a hinge. A hinge is made of metal. That's an example of a conductor, right? It has a certain shape. The knob on my door would be another example of something that's a conductor. It's probably pretty solid all the way through. On the handle of my door, on the knob of my door. Anything you can think of that's metal, a piece of metal that's solid. It could be a ball of foil, right? Aluminum foil is a conductor, right? If you take a piece of aluminum, you crunch it up into a ball, that's going to be a conductor, right? So that's what we're talking about here. So it says the electric field is zero everywhere within the conductor. Let's see if we can understand why that would be the case. So in order to have an electric field, you need to have charges, right? You just absolutely have to have charges. So let's say that we have some charges. And let me say that at first, let's assume that one side of the object carries a lot more charges than the other side of the object. So let me say that I tell you that at one point in time there's a conductor that looks like this. There's a whole lot of charges on the left side, not as many charges on the right side, right? What do we know about conductors? What is it that defines a conductor? Electrons are free to move, yeah. Charge flows easily. Some sort of flow. That's all right, exactly. Charges flow easily. Charges flow easily. Excess charges flow easily. So electrons in general are the charge carriers. I find that it's often quite difficult to talk about electrons, and it's easier to just assume that the charges inside of here are positive, and that the positive charges can move. I can explain that when a positive charge moves to the right, it's actually an electron that moved to the left or something like that, but I think that gets kind of complicated. So let's just assume for now that the conductor carries excess positive charges and that these positive charges can be moved around as we please, right? Now, if I told you that this region on the left had more positive charges than this region on the left, right, and we think about one of the charges, right? We look at one of these charges right here. Do you think it's likely that this charge is going to stay here? If there's more positive charges on the left than there are on the right, and I tell you that charges can flow very easily with almost no restriction, it's extremely unlikely this is going to stay still. It's very likely that it's going to move over here and try to fill in this region on the right. Because by doing so, that'll create more of a balance, right? Now, if this particle has to move, we've already kind of violated one of the initial conditions of our system here, right? What are we talking about? We're talking about conductors that are in equilibrium. Not thermal equilibrium, but electrostatic equilibrium, which means that the charges can't really be moving around. If it's in equilibrium, they can't be moving around. So this original state that I've given you right here, this is a non-equilibrium state, right? It's not in equilibrium. There's no way. Because we can immediately see that there should be some forces here that should rearrange these things, right? There should be some forces here that should rearrange these things. Okay? So, if that's the case, then where are the objects going to move? Well, I would think that if this object wants to go somewhere to get as far away from these other charges as it can, where is it going to go? It's probably going to go all the way to the surface, right? Because that's as far as it can get away, right? In fact, I would assume that all of these charges would really tend to want to get to some kind of a position where they were basically equally balanced with each other. And the only way that that can really happen is if these charges start to move themselves, well, towards the surface, pushing them, spreading out as much as they possibly can, really. After all, if there's a region where the charge density is too much, right, these charges pretty much have to move away until they find some balance, find some equilibrium, right? Find some equilibrium. So suppose we've reached an equilibrium position now. Suppose that now what we have is some kind of equilibrium situation where now charges do not move, right? Equilibrium means charges don't move. That's what that's going to mean. The charges are basically going to stay still. They're roughly going to stay in the same location, okay? So suppose that we've reached that equilibrium state and the charges are all spread out like this. Now suppose that I take another charge and I try to add it to my system, right? And, you know, let's say that I try to add it to my system, like, I don't know, somewhere right here or something like this. So if I'm in a situation where everything's in equilibrium, then this charge, if I was to place it in here, and let's say that it's a test charge, so I'm going to place it in here, but I'm not going to disturb the system. If I were to place a test charge in here, and I told you that the electric field inside was not equal to 0, so I tell you the electric field in here is not equal to 0, right? You don't know if I'm telling you the truth or not, but I tell you the electric field inside here is not equal to 0. I place a test charge in here. What is that test charge going to do? If the electric field has some value, what's it going to do? Like if I tell you the electric field is not 0, and that at this location there's a net electric field that points off in this direction. Let's say we make that assumption. Let's say that's the direction of the electric field. What's the test charge going to do? It's going to go in the direction of E, right? So this test charge is going to tend to flow over to this side right here, right? It's going to move like that. Okay. Well, if the test charge moves, if I tell you that that electric field in there points to the right and the test charge moves, what about this charge right here? Shouldn't it also move? And this one right here, shouldn't that one also move too? And if we do that, right, and we say, okay, let's assume that there's a field inside of there, all of a sudden what we're going to find is every single charge that's over here on the left-hand side is going to start piling up on the right-hand side. Would you all agree with that? If in fact there's an electric field inside of here, any piece of charge is just basically going to have to push its way to the right-hand side, right? Would you all agree? And then if we do that, we're going to be back to the state of non-equilibrium, right? If I continue to pile extra charges over here on the right-hand side, we're going to be in a situation where, guess what? When you're in this region of space over here, what's the electric field going to look like? If there's all these positive charges packed up on the right-hand side, would you all agree that now all of a sudden the electric field inside has to point to the left? Does that make sense? Because we're right back to where we were before. We have a bunch of charges. They're all bunched up. They don't want to be bunched up. Charges flow easily. So really there's going to be now like a rebound effect that occurs, right? So if I told you that initially there was an electric field inside of here, it would then cause charges to move to the right-hand side, which would then reset the condition where now there's an electric field on the right-hand side that pushes them back to where they were before. So this process basically would just continue until we reach a state where the electric field inside has to be zero. There's no other possibility. Because if it's not zero, then everything is going to flow until it basically becomes zero again. It's basically going to flow until it becomes zero again. So the only way for the system to actually work, the only way for there to be real equilibrium that involves charges not moving all over the place, the only possibility is that the electric field is equal to zero. And if it's not equal to zero, okay, the charges are going to redistribute themselves until it equals zero. And this is, yes, it's all a consequence of the fact that the charges can move around easily and the fact that the charges themselves can produce electric fields, right? So to summarize the argument goes, suppose that it's not zero. If it's not zero, then the charges are going to shift to the other side until it becomes zero again. That's pretty much the idea. I can give you another example of this. Something that when we go into the lab this week, I will show you this. I didn't show it to my last group because we hadn't talked about it in class yet, but let's do number 2 first, and then I'll talk about it. Okay, so for now we're saying the electric field inside is zero everywhere within the conductor, whether it's solid or hollow, okay? Whether it's solid or hollow. If it wasn't zero, the charges would rearrange themselves such that the electric field inside, once again, would become zero. Now, when it says hollow, what they mean by that is even if you had a surface, okay, that was hollow on the inside, so if you had like some cavity here, you know, that was, I really don't know how to draw this I can't draw it. I'm not good enough. Your book has pictures of this, but imagine if there was like a hole cut out of the center of this. What I'm thinking of is like, you know how a tennis ball is hollow on the inside? Because there's like a thick outer wall and then it's hollow on the inside? It'd be the same concept here. That if you were to chop a hole out of this object, like cut a hole out of the middle, the electric field inside the conductor and inside the hole would also be zero. That's what they mean by that. All right. So because the charges can flow, the electric field inside has to be zero. That's number 1. Does anyone have any questions? I'll stop for now. This one is extremely important. It's extremely important. You will see this show up on homework problems over and over and over again, that they are going to assume you know that the electric field inside of a conductor is zero. So this is just one of those conceptual concepts that you need to memorize. Okay. So any questions? For number 2 says, if the conductor is isolated and carries a charge, the charge resides on its surface. For this, we can use Gauss's law in combination with Rule 1 to prove that this is true. This basically says that if you have a conductor, all the charge is going to be on the surface, which is kind of how I tried to draw it here. We decided that this arrangement was actually the only arrangement that would produce a zero electric field. But using the fact that the field is zero inside of here, we can make the following statement. Suppose that I chose to draw a Gaussian surface on the inside right here, okay? So I draw a Gaussian surface of some kind. Maybe I draw a cube or something. And number 1 tells us that at all places on this cube that the electric field is equal to zero. If I know that I can draw a Gaussian surface, and I tell you that the electric field on that surface is zero, how much charge has to be inside, according to Gauss's law? In order for the electric field to be equal to zero. How much charge do I need to have in the box in order for the electric field to be equal to 0? 0, right? The charge enclosed has to be 0. That's the only option. Now, that's going to work up until I make my box big enough to include... Oops. Select the whole box. Until I make my box big enough or move it around to include the inside and the outside of the box. Because as we know from the problem, one of the problems we did earlier, the electric field out here should be not 0. It should have a value. There is going to be some electric field out here because I can draw electric field lines, right? I can draw electric field lines pointing out like this. Whoa, did it really change colors while I was writing? I've never seen that one before. That's a new one for me. I didn't want to change the color of the other one. It was green, right? Okay. Sorry. I know that I can actually draw electric field lines out here. I love that it does that for me. It's so nice that it just plops in. Oof. I can draw electric field lines surrounding this object. So I know the electric field out here is going to be non-zero. After all, I could draw a Gaussian surface around the outside of this and it would enclose charge, right? So that statement of the Gaussian surface having 0 charge inside of it, it's only going to be true as long as I draw the surface inside the object. Okay. But what I was trying to say is that I could take this cube and I could reform it to have the exact same shape as my conductor, right? And then I could draw a Gaussian surface by basically making it so that my Gaussian surface came right along the edge of my conductor right here. Okay, I'm going to erase this line. But if that was my Gaussian surface, how much charge should be contained in that? Well, I know the electric field has to be 0 everywhere on this Gaussian surface because that's what number 1 tells me. We're inside the conductor, right? So if the electric field is 0, that means the Gaussian surface is 0. These basically go hand in hand with each other. When the electric field is 0, the Gaussian surface is also... Sorry. When the electric field is 0, then the charge enclosed by the Gaussian surface has to be 0 as well. And so that kind of proves number 2. That if the conductor is isolated and carries a charge, the charge resides on its surface. Does that argument make sense? No charges on the inside means that all the charge has to be on its surface. I feel like this stuff is so hard to describe when I can't use my hands, when I can't use three-dimensional objects. I hope you all are keeping up. The important part here is to learn like what the rules are and then try to understand why they're true. Anyway, so going on to number 3, please, if you all do have any questions, please let me know. For number 3, what I'm going to do is we're going to draw a new surface. So now, let's say that we have our conductor, okay? Let's say it's shaped kind of like this. It carries positive charges. And I'm going to say that as the conductor starts to get a little bit curvier, the charges get a little closer together. And they spread out again along these flat parts. All the charges, as we know, have to be on the surface itself. We can't put any charges on the inside. But I'm just going to say that the places where it gets kind of sharper, where the curvature gets higher, the charges are going to go up in density. Okay. Now what I can do... Sure, Josh. So yeah, if I made a Gaussian surface like around this, it would include the total charge. Yeah. That's right. Okay, so for number 3, if I wanted to find what the electric field at a point just outside a charged conductor is, what I have to do is I have to draw a little Gaussian surface. So I'm going to draw one here. My surface is going to enclose just a portion of the surface of our object. I'm going to say that the area of the cap on the top is going to be A. I'm going to draw some electric field lines in here. Our electric field near here is going to point... Well, how is it going to point? We don't really know. So let's start off by assuming that the electric field comes up at some angle right here relative to the surface. So there's some angle right here that's not a right angle, okay? Let's assume that this is our electric field, okay? If we do that, that means our electric field is going to have 2 components. One of those components is going to point perpendicular to the surface, like this. and the other component is going to point parallel to the surface like this. Would you all agree? If I just take some random point on here and say the electric field goes this way, well, that could be broken up into E perpendicular that goes this way and E parallel that goes this way. Do you all agree that we can do that? There's going to be some component perpendicular to the surface and some component that's parallel to the surface. If I just pick that the electric field here goes this way. So then what we think about is, suppose we think about one of these positive charges that's sitting here, this one or this one, for example. If in fact there is a field that's parallel to the surface, what's the direction of the force, let's say, on this particle going to be? Right here. What would the direction of that particle be? If I tell you that this electric field, that there is a component parallel to the surface, what would the direction of if the electric field here is this way, if there is a parallel component of the electric field that points this way, what's the direction of the force on a positively charged object inside of there? That's not a good answer, Daniel. I want left, right, up, down, forward, backward. Up? No. Why? It's parallel to the field, exactly. Yeah. So if I tell you that the electric field points like that, then the direction of the force is the same direction. Remember, electric fields and electric force are a very simple connection. If I have a force, if I want to find the electric force, you just take the charge, you multiply by the field. So if it's a positive charge, the force and the field are in the same direction, right? Okay, so if there's a parallel component to the electric field, a positively charged object is going to feel a force that's going to point this way, right? So if there is any component of the electric field that points to the right, then there's going to be a force on these particles, which means that these particles are going to tend to not stay in the same place. But we're assuming that we're in equilibrium. We're assuming that the particles are static, they're not moving, right? So if you have any parallel component to the charge, to the field here, it's going to produce a component of force that's going to point along this surface, which means that these charges would need to circulate around the surface, basically, right? That's what would have to happen. But that's not possible because we're in equilibrium, it's supposed to be static. That means that the parallel component of the field has to be equal to 0 at the surface. Has to be equal to 0. So when I come back here and I think about my Gaussian surface then, I know that my electric field vectors cannot point at an angle. They have to be perpendicular to my surface now. Because if they weren't, it would cause the charges to circulate around. So now what I know is that this has to be the only component of the electric field here. That all of my electric field lines are going to be perpendicular to the surface. Like that. They will all be perpendicular to the surface. And not like this. Basically saying that this is not possible. You can't have this perpendicular component. It has to all be pointing away from the surface. And then we can use Gauss's law and say, we know over here the electric field is equal to 0, up here is equal to this. Gauss's law says, perform this operation. And if I tell you the surface charge density at this location is sigma, that means that the charge enclosed is going to be sigma times A over epsilon naught. And for E dot dA on the left-hand side here, what we're going to have is that across the top, you're going to get a flux of E times A. Across the bottom, you're going to get a flux of 0. And on the curved side, you're going to get a flux of 0. So we get this. And then it tells us that the size of the electric field after you cancel out these areas is equal to sigma over epsilon naught. It's basically the same solution that we got for the infinite plane, except that now it's a finite plane, and now sigma represents the surface charge density at that location. Okay? So this sigma, right, read this right here, it says, the electric field at a point just outside a charged conductor is perpendicular to the surface. We proved that part by saying that otherwise the things would circulate around. And has a magnitude of sigma over epsilon naught, which is what we got right here, where sigma is the surface charge density at that point. At that point. So now we know exactly what the electric field is near the surface of a conductor as long as we know something about the charge density. And one thing I'll say here is that that electric field has to be perpendicular everywhere. So anywhere you have a surface here, the electric field is always going to be perpendicular. Over here it's going to point like this, like this, like this, like this, perpendicular at every single point of the surface. And I'm just going to say the last one, number 4, basically states that if you have a sharp point, then the charge density in the sharp point is going to be a lot higher. There's going to be more charges packed in there. And because the charge density is higher, that means that the electric field's higher. And number 4 basically says that on an irregularly shaped conductor, the surface charge density is the greatest at locations where the radius of the curvature of the surface is the smallest. That means where you have this really tight spike, right? And one consequence of this is that if you have a conductor and it comes down to a point, like I guess I can use my pen as an example of this. If this pen was a conductor and it came down to a point like this, in fact, I'm going to show you something in class that looks exactly like this, except it's going to be made of metal. I'm going to use it to produce a lot of like electrical shocks. I'm not going to shock anybody with it, but I'm going to show you some of the properties. Anyway, so if I have a metal and it carries electric charge, the place where the electric field is the biggest is going to be the place where there is a very sharp point, right? Like on a pen, where a pen comes down to a very sharp point. And if you think about the way that shocking works, like if you want to shock somebody, the easiest way to shock somebody is like with the end of your finger. Because if your body carries excess charge and you want to shock someone, it's harder to do it with like your palm. It's much easier to do it with your finger because your finger has a high, radius, has a small radius of curvature, which is to say that it's very sharp relative to your palm, which means your finger is going to be very good at delivering electrical shocks. That's kind of what the last two statements say. Because the bigger the electric field is, the more likely you are to be able to. Yeah, I think so. That's probably part of the reason why it has a sharp probe. Also, so that you can pinpoint exactly. I think it's the multimeter. It's more, I think, so that you can touch a very specific point on a circuit or a very specific point, like in the lab that you were doing on that graph. I think it's more for that. But in terms of its sensitivity, it could have something to do with that as well. It's probably more sensitive if it has a sharp point. So that would make sense. So these 4 rules are just referred to as the rules for conductors and electrostatic equilibrium. I didn't take this list from your textbook because your textbook tells you all this information, but it kind of spreads it out over multiple chapters. And you really do just need to know all these 4 pieces of information because they're going to keep coming up over and over again. So if you open a car door with more surface area in my hand, I'm less likely to shock myself. Yeah, it's kind of hard to do though, right? I mean, you generally have to stick your fingers up under the door to open it, right? So, but if you could somehow increase your surface area by like wrapping your hand in a cloth or something like that, it would actually reduce the thing. Yeah. Daniel, is your picture from a Stone Temple Pilots album? Is your profile picture from a Stone Temple Pilots album?
Yeah, it is.
Do you like the Stone Temple Pilots?
Yeah.
Oh, I didn't know anybody listened to them. I love them. That's like a band that I really liked growing up. I have all of their albums. They're really good.
Wow, that's cool. Yeah. Purple, like every song on Purple is perfect. I don't know.
Yes, I would agree. All right, so what time is it now? How much time do we have left? 4 o'clock. Good. We have more time. So we're going to do one more example of a Gauss's law problem that's going to employ some of these ideas and see how you would actually apply these ideas of conductors in electrostatic equilibrium. So let us do it. That's this problem right here. I know for a fact that you have a homework problem that is very similar to this. Homework problem may be easier than this one, I don't know. Much like all the other examples we've done today, this comes from a different textbook. All right, so a sphere inside of a spherical shell. This is the one we want to try. So it says, a solid immediately, you see the word insulator now, and you need to remember that that's important, right? So a solid insulating sphere of radius A carries a net positive charge, capital Q, uniformly distributed throughout its volume. A conducting spherical shell of inner radius B and outer radius C is concentric with the solid sphere and carries a net charge of negative 2Q. You can kind of see that on the picture here, maybe not so obvious, but here's our insulating sphere. That's this one. And then the blue one is the conducting sphere. Okay, so insulator is red, the conductor is blue. And we're given the charge on the insulating sphere is capital Q, and the total charge carried by the conducting sphere is negative 2Q. The two objects are separated by air, so air is an insulator. So it's not going to allow the charges to flow very easily from the inner sphere to the outer sphere. So they're basically disconnected. So you have negative 2Q on the conductor, positive Q on the inner object. And what we want to do is we want to find, by using Gauss's law, use Gauss's law to find the electric field in the regions labeled 1, 2, 3, and 4. So that's inside the insulator, in between the two objects, inside the conductor, and outside. Those are the three situations. We've actually already done part of this. And so for that part I will... Technically we've already done all of it, but we just need to put everything together basically. Alright, so let's go through this. We're going to go 1, then 2, then 3, then 4. So we're going to start with region 1. And I don't know what to do here. I don't know if I want to redraw the picture or what. If I want to draw it bigger and then draw on the picture. That's kind of what I want to do. We'll need to make multiple copies of this to do that, though. And I guess it would probably make sense if I also tried to do something like just got this part. That way I could leave this here so we don't mess with it too much. And then on each part we could just draw on the figure. I think that makes the most sense. Okay, so for part 1, we're going to be finding the electric field for the region of R less than A. In order to do that, we need to draw a Gaussian surface inside, right? So if I want to find the electric field at a region less than A, I've got to put a Gaussian surface inside of there. Maybe this will show up well, will it? Nah, not really. That's hard to see. Maybe we'll just do red or something, or like green. Hey, look, it didn't change. What do you know? Oh, that's cool. Alright, really? So I click away, push some buttons, try it again. There we go. Alright, so this is going to be my Gaussian surface. We're going to draw it inside of here. I need to squeeze it a little bit to make it more like a... There we go. That's going to be my Gaussian surface right there. Can't really see it very well, but there it is. We need to draw it so that it has a radius less than A. We'll define the radius to be R. What are the electric field lines going to look like in this region? We did this a little bit earlier. What are the electric field lines near this going to look like? It is a positive charge, by the way, on the inside. Positive charge Q. They point away from the center, exactly. So I don't want to draw a lot of field lines on here. I don't feel like I need to, but you all understand that these field lines, they tend to point out and away, like this, right? I'm just going to draw one. And we also know that on the surface of the sphere, the direction of dA is going to be in the same direction, right? So dA is going to point in the same direction, which means that E dot dA is basically just equal to EdA. That's probably, right? And then we go through and use Gauss's law. So we're still doing section 1 here. Gauss's law says do this. On the left-hand side, we can say E and dA are parallel to each other. The electric field should be uniform. So we're going to end up reducing that down to just EdA, which is going to become E times A, which is going to be the surface area of our sphere. On the right-hand side, Q enclosed. This was one we did earlier where we said that in order to find the total amount of charge that's enclosed inside of here, what I have to do is I have to take the total charge, right? And I have to multiply it by a ratio of the volumes, where on the numerator I take the volume of the Gaussian surface, and I divide by the total volume. And then we obviously have to divide that by epsilon naught. So what we're going to get is, on the left-hand side, the area we're talking about here is going to be the surface area of our Gaussian. On the right-hand side, what we have is Q times V Gauss over V total. So that's going to be something like 4 over 3 pi times the volume of the Gaussian is going to be A cubed. We divide that by 4/3 pi times the total. No, I mixed them up. I'm so sorry. I really should not do that. That's right. The Gaussian has a volume of 4/3 pi A cubed. I did it twice in a row. The Gaussian has a radius of R. So the Gaussian has a radius of 4/3 pi r cubed. The total volume, which is going to be the volume of just the red object right here, is going to be a cubed. There we go. And again, that's all divided by epsilon naught. Scoot down a little bit here. So when we plug all our numbers in, we're going to get that. These cancel, so you're going to get q r squared over a cubed. Sorry, this is still cubed. R cubed over a cubed. Put the epsilon naught in the denominator. Cancel out those and one of these. And what we end up getting is that the electric field is going to be equal to q over 4 pi epsilon naught a cubed times r. And this is for the region of r greater less than a. Same result we got earlier. Any questions about that? All right. Region 2. Paste. 9/3. What's up? What do you mean? 9/3? This one? 9 divided by 3. What are you talking about, Johnny? Can you help me out, please? Yeah, sometimes when I'm writing things, it will connect the top of my 4. So if I write a 4, it'll sometimes like connect the line right there. It's just a 4. Sorry. I'm sure you've seen that happen before. All right, now we are into region 2. So we recopy this down. We're now looking at region 2. Okay, so let's shift this over to here. This OneNote application is getting very unresponsive, so bear with me. Region 2, right here. We've already got a dashed line right there, so let's call that our Gaussian in order to not draw extra lines on here. So let's say that's our Gaussian, right? It encloses all of the objects. This is going to be for the region of A less than R less than B. B is the inner radius of this portion right here. So we can now say that our electric field lines, right? Our electric field lines are going to point out like this. Our dA vector is going to look something like this. They're going to be parallel to each other. So what we're going to do is we're now going to say, again, integral E dot dA is equal to charge enclosed, divide epsilon naught. So the left-hand side is going to reduce down to E times A again, because E and dA are parallel to each other, and because it's very likely that along this dotted line right here that the electric field will be uniform. So what's the charge enclosed now by my Gaussian? Q. Yep. So here we just have Q over epsilon naught, and all we have to do is to plug in the surface area of our sphere, which is going to be 4 pi times the radius of the Gaussian, which is r squared, and then keep going until we have Q over 4 pi epsilon naught r squared. This is for the region of A less than R less than B. Okay. We've technically already done these two calculations today, but I think it's often useful to go through them again so you can pick up on details that I might not have said before. Next is the part that's kind of new. So the next part we want to do, obviously, is region 3. Let's give it 20 minutes to paste the copy of the picture in there. There it goes. Okay, so next we want to do region 3. For region 3, this is a little trickier. We need to draw a Gaussian surface. Where do I need to draw it now? If I want to find the electric field in region 3, which is inside of this piece right here, how do I need to draw my Gaussian surface? Where should I draw it? Should I draw it like right here? Should I draw it like that way? Region 3, how do I want to draw the Gaussian surface? A circle with the same center, that's exactly right. That's a very good way of putting it. So I need to draw inside of here a circle that fits in. Oh wow, I made it like the exact same size. Just need to make it a little bit smaller, that should work. So I need to draw a circle, kind of fit it right around like that, right? Not perfect, but we need to somehow get it right in between. Okay, so now that's my new Gaussian surface. It's not on the surface, it's inside the surface. Okay, there's my Gaussian. Now, this is the part where things get kind of tricky. What should the value of the electric field inside the Gaussian be? What should it be? What should the value of the electric field inside of here be? And remind you, the blue piece is a conductor, so it should be 0, right? So that is the answer, but we kind of need to prove it a little bit. Not really. We've already proved that inside of a conductor, the electric field is going to be 0, but I'm going to try to draw some lines on here to help you understand why this is the case. First thing I'm going to do, too, is to say, we know that Gauss's law, if we actually tried to do this, Gauss's law would say that E dot dA would be equal to Q enclosed over epsilon naught, right? So what does Q enclosed need to be now? So the charge enclosed by my Gaussian, what does Q enclosed have to be if this is true? Like, in order for the electric field to be equal to 0, what does Q enclosed have to be? 0, right? But we know that if we look at the red object right here, right? We know that there is charge contained by the Gaussian surface, right? How much is there? How much charge is contained by the Gaussian surface of this red object, of the insulator? At least Q, right? So how can it be the case that I tell you that the charge enclosed has to be 0, but there's a total charge positive Q right here? Something else has to be going on, right? Yeah, what about conservation of charge? What can you do with that? The inner blue circle has negative Q. That is exactly right. So we know that the blue object carries a total charge negative Q, right? But we didn't say anything about how that charge is distributed, right? So if you have a positive charge here, right? Let me draw some little plus signs on here. We know that this part is positive, right? There's positive charges inside of here. In fact, they're uniformly distributed. So isn't it reasonable to think that some of the negative 2Q right here might go to the inner surface right here? And when you say how much, well, if I know that the total charge has to be equal to 0, like if I know that Q enclosed has to be equal to 0, then this has to be equal to the amount of charge that exists on the inner portion of the conductor. Q inner plus the total charge on the insulator, right? Q inner would be the charge on the inner portion that I'm drawing here, all these negative charges that have been drawn to the center, right? And if that's the case, then that means that Q with a negative sign in front of it has to be equal to Q inner. I don't know, does this problem actually ask us to do that? I think it does at the end. Yeah, one of the things that it wants us to do is to also find the electric fields and the charge distribution on the shell when the entire system is in electrostatic equilibrium. So we've already partially figured that out. We figured out that the charge on the inner shell has to be negative Q. How much charge is going to be left for the outer shell then? We know the total, if I take Q outer plus Q inner, that this should be equal to negative 2q, right? So if this one is already negative q, then the charge on the outer portion of the shell also has to be, if I do negative 2q plus q, right, we get negative q again. So now we know that there's a negative charge distributed on the outside. And the way that it's distributed is on the center, right, in the middle, this part we have a total charge of capital Q. When we get to the inner ring carries charge negative Q, and then the outer ring carries a charge of negative Q as well. Of course, it's spread all throughout, right? It's negative Q spread all throughout here, and then negative Q spread all throughout here. I'm not doing such a good job of drawing it, but do you all understand the idea? You have problems like this too that you have to do. May not be the same kind of numbers, but yeah. This problem is unique in the sense that, like, if we change the Gaussian to have a total of negative 3q, the inner portion would still be negative q, but the outer portion would be how much? Like, if I told you instead of negative 2q that this was negative 3q, if I just said that's how much there is, I'd just give you a different problem, right? Then this would become 3, this would become 3, and there'd be a 2 right here. So you'd have 2q on the outside. So that's the kind of stuff you're going to see show up in your homework, is it'll be slightly different than this, but if you follow the procedure, you should be able to solve these type of problems. All right. That's pretty much the end. We also are supposed to find the electric field in the fourth region. The fourth region is the very outside region. And for the fourth region, I'm just gonna say, well, we're gonna need to get the picture again. Even clicking it takes forever. Like even selecting it. I really wonder what it is that makes it so slow. I'm just assuming that it's probably the RAM on my computer or something like that. Okay, for part 4. Come on. Now we have to do another region. We need to put a Gaussian surface outside the whole object. And now we go through the same process again. We do integral E.dA has to be equal to charge enclosed divided by epsilon naught. But now the charge enclosed is going to be negative 2q plus positive q. Right? Because there's a total negative 2q plus positive q. All the other stuff doesn't really matter. Once we're outside, we're looking at our Gaussian now. This is our Gaussian again. Okay, so then again on the left-hand side, we're going to end up getting E times A again, and it's E times 4 pi r squared. So you get E is equal to negative q over 4 pi r squared epsilon naught. And there we go. That's it. This is, what is this? R greater than C. Okay. And that's it. That's time. Is it 4:20? Did we get to, or 4:25? I think we might have like 5 more minutes, which we can just spend to kind of like digest this problem. Okay, so definitely going to see these kind of problems on your homework. You'll also see these problems like this on exams too. Good Gauss's law problems that involve you to kind of like not only use Gauss's law, but also to apply some of these concepts about conductors and electrostatic equilibrium. I just want to emphasize a couple things you have to take away from today's lecture. Hopefully one thing you take away is you have an idea of how to solve Gauss's law problems. And the other thing I hope you take away is these. The rules for conductors and electrostatic equilibrium. The main things to memorize are electric field inside is 0, all the charges are on the surface, electric field is given by this, and it's always perpendicular. Those are the 3 ideas. And we'll prove number 4 later. Okay, any questions? Now is a great time to ask questions now that we've completed all of this and we have some time. Okay, you too. If you didn't come, remember, if you didn't come last week for the lab, you need to come this week for E-42. And we have an exam the following week, so everybody will come. All right, thank you. No questions? Someone's got to have a question. Tomorrow at noon I have office hours, yes. You are welcome. I really thought we would get to electric potential today, but it takes so long drawing some of these pictures. There's not much I can do about it. Okay, it doesn't seem like there's any questions, so I guess we'll stop just a little bit early today. Yep, you should be able to complete homework too. I don't see any reason why you can't. Should be able to. All right, stop in the